What is attenuation? Attenuation nothing but transmission loss. When the signal is propagating through the optical fiber, there is some power loss occurs due to different mechanisms. The transmission loss or transmission of power of the signal when it is propagated through the optical fiber is called attenuation. And if you take an optical fiber and the power coupled into the fiber is for suppose P naught, that means at the starting end, P naught power is coupled. Then when the signal is propagating through the fiber here, the power decreases exponentially with the distance here. So the power decreases exponentially. So after traveling z kilometers here, the optical power is P of z. What is the P of z? The optical power after traveling z kilometers through the fiber. And P naught is the input power. Now, how the how the optical power varies with z here? It varies exponentially with z. That can be written as P of z equal to P naught into e power minus alpha P into z. So this minus represents the decreases and e power represents the decrease exponentially with the distance here. This alpha P is called attenuation coefficient. Alpha P is called attenuation coefficient. And if you take this P naught here, P of z by P naught is equal to e power minus alpha P into z. Then take the reciprocal, then minus will be cancelled. Then take log on both sides and simplify. We can get alpha P equal to 1 by z log P naught by P of z. The units are per kilometer, but generally we are expressing in terms of decibels the power ratio. That's why we can express the attenuation coefficient in terms of decibels per kilometer as 10 by z log P naught by P of z. 10 by z log P input by P output. That is the attenuation coefficient here. There are three mechanisms involved in this one. The three mechanisms are: one is absorption, that absorption related to fiber material. Next, scattering, the scattering related to the fiber material as well as structural imperfections. And third one, radiation, that is due to the perturbations of the fiber geometry. That means bending of a fiber. Coming to the absorption, the three different mechanisms cause this absorption. One is impurities in the fiber material. So what are the impurities present in the fiber material? Those are responsible for the absorption here. This absorption, because of presence of transition metal ions inside the fiber or presence of hydroxyl ions, OH minus ions. If the OH minus ions are present in the fiber, those OH minus ions are highly absorb the wavelengths 2700 nm, 1400 nm, 950 nm, 725 nm. So if hydroxyl ions are present in the optical fiber, those are appears in the fiber during the manufacturing process. That's why we can't avoid them. But those ions are responsible to absorb these wavelengths because they're having high absorption at these wavelengths. So that's why never use these wavelengths for optical communication purpose, because at these wavelengths the absorption is very, very high. That's why there is a more transmission loss occurs, more attenuation takes place. And because of presence of impurities also, the photons in the light beam collide with these ions, maybe they can excite the electrons. So that is also responsible here. And these hydroxyl ions are creating big problem at these wavelengths. So never use these wavelengths for information carrying. Next, second absorption mechanism is intrinsic absorption. That is fiber metal itself. That means what are the atoms present in the fiber material that are used to design the fiber. For example, if we take silica, that is SiO2, there silicon ions or silicon atoms are responsible for this absorption of the light beam. For example, if you take electronic absorption band of silicon, they will absorb UV regions. Or atomic absorption bond occurs in the IR region. So mostly we are using IR region for optical communication. There what happens, atomic bond vibration. That means because of these photons, the atomic bond vibration takes place. That's why what happens, some photons are absorbed. Then optical energy converted into vibrational energy. So because they are vibrating atomic bonds between these silicon and oxygen there. And third kind of absorption is radiation defects. The radiation defect means if you light down the optical fiber in the region where more radioactivity is there, that means there is a chance to get more alpha, beta, gamma particles presence of some radioactive material. Those alpha, beta, gamma particles are creates defects in the fiber. That means by hitting the fiber material, these alpha, beta, or gamma radiations can create some defect. That means they can remove some atom from that one. That halo region can absorb some optical energy or by some internal reflection at that halo region. So that is also responsible for some kind of absorption. Next kind of next kind of attenuation mechanism is scattering. The scattering is due to variation in the material density. That means one area, the material density is high when compared with the other area. There may be change in chemical composition. There may chance to have some chemical composition variation in the one area, or there may be structural inhomogeneity. That means there may be the diameter may be less or diameter may be high. Okay, because of the three reasons, one is variation in material density and our chemical composition, or maybe structural inhomogeneity. That means there may be change in diameter here, there may be chemical composition change here, or there may be density change here. Those are creating, those are acts like a scattering centers. So they scatter the light. The scattering is two types here, linear scattering. In the linear scattering, the energy in one mode transferred to the other mode at the same frequency. Or non-linear scattering. In the non-linear scattering, the energy in one mode transferred to the same mode or different mode at different frequency. That means in the second case, there is a frequency shift occurs also. There may be chance to get some phonons with photons also in non-linear scattering. So linear scattering, again two types, Rayleigh scattering and Mie scattering. And non-scattering, they are stimulated Boolean scattering or Raman scattering. So all these are responsible for scatter the light. But once they are scattered here, the energy can be shifted from the one mode to other mode. That other mode may be leaky mode. Then the energy loss occurs here. Another one is radiation loss, that nothing but bending loss. So radiation loss occurs due to the bending of fiber. The bending may be macro bending that occurs when the fiber takes a turn, or the bending may be micro bending that occurs when the fiber inserted in the cable. So radiation loss due to bending of fiber, that may be macro bending or micro bending. Macro bending when fiber takes a turn. Micro bending when the fiber inserted in the cable. In case of macro bending here, if you take a single mode fiber, for suppose, then what happens? The optical ray is passing through the radius of the core. But around that, what happens? Field distribution takes place. So this is the electromagnetic field distributed around this ray propagation. So this field distribution makes to enter some field in the cladding also. That means the total field is not passing to the core only. There is some field entering to the cladding also. Even though some field entered into the cladding, that will drag by the field which is passing to the core. That's why even though some field entered into the cladding also, there is no problem. That field will be dragged by the field passing through the core. But if the fiber bends, then what happens? More field comes out of the core. If the ray is propagated to the core, then up to certain distance from the core axis, the field will be dragged by the field passing to the core. If the field goes out more away from the core axis, that means that crosses a certain distance. That distance can be named as critical distance. Then what happens? What is the field going out of the core, that field can't drag by the field passing through the core, then that field will be radiate out. I will give some simple example by this picture here. If you observe here, because of this bending, so because of this bending, here more field is going out here. Up to a certain distance, that is called critical distance, that XC, that field can be dragged by this field passing the core. But if you observe this field, that field is away from the core, which is crosses the distance of XC, that is critical distance. Then this field will be radiate out. So in this way, radiation loss occurs here. That depends on the bending of this fiber. That means the radius of curvature of this bending. So the radius of curvature is high, the bending is low. The radius of curvature is low, that means bending is high. That's why there is a critical radius of curvature, RC. It is bends below RC, the radiation starts here. Bends above RC, that is not a problem. That's why while you are light down the fiber, you should be careful how much bending it takes here. The bending is less than critical radius of curvature, the radiation loss will not occur. If it is below the RC, the radiation loss is high. Above the RC, the radiation loss are not occurs here. That's why never bend the fiber such that the radius of curvature of the bending is less than the critical radius of a curvature. Less than critical radius of curvature is not allowed. Above this one is okay. And sometimes the bends will occur when the fiber is inserted in the cable. When the fiber inserted in the cable here, there is some bends occurs. That bends are called micro bends. Because this micro bending, there is a chance to get mode coupling. When they when the mode coupling occurs here, the coupled mode may be leaky mode. Some energy loss occurs. In this way, the bending also respond for attenuation, that is known as bending loss. So by considering the three, absorption, scattering, and radiation, the total attenuation will comes like this. If you observe here, these peaks, this one correspond to the 950 around, and this peak correspond to the 1400 here. These peaks are because of presence of hydroxyl ions here, OH minus ions. That's why I told. See, if you see this peak of attenuation, that is very, very high at these wavelengths because of hydroxyl ions, OH minus ions absorption. That's why I told never use those wavelengths. So if you observe this region 800 to 900, this wavelength is okay. So use 800 to 900 nm wavelength for optical fiber communication, or we can use from 1250 to 1350, or we can use in between 1500 to 1600 nm. If you take 800 to 900, if you observe that attenuation when compared with the 1250 to 1350 is high, but wavelength is low means frequency is high. Frequency is high means bandwidth is high. But in 1250 to 1350, attenuation is very, very less, but frequency also less. That's why there is a less bandwidth. So based on the requirements, you have to optimize which wavelength is suitable for us. That's why while designing the fiber for communication purpose, you have to optimize by considering the attenuation and considering the bandwidth and what is the capacity is required for information carrying. That also we have to estimate. And now we are going to discuss about optical fiber communication block diagram. If you observe the optical fiber communication system block diagram here, there is a transmitter and there is a receiver. Both are connected through a optical fiber cable here. And in between this one, here this regenerator, the regenerator is to reshape the signal, because we know when the signal is propagated to the optical fiber, the attenuation makes the signal to lose its power. So how much power loss that we have to make to regain by the signal again to travel for long distance. That's why we are using these regenerators to reshape the signals and repush their actual power and make them to again travel. So now in transmitter, if you observe here, there is a driving circuit and light source. Here, this one is the electrical signal. This is the electrical signal we have to send. Then to send this electrical signal, first of all, you have to superimpose this electrical signal onto the optical carrier wave. For that purpose, what we are doing is we are taking a light source. The light source may be LED or semiconductor laser. And that light source, we are connecting a driving circuit. And for the driving circuit, we are giving the electrical signal as a input. Then what will happen? The electrical variations are converted into optical variations. How it will happen? The driving circuit drives the light source in accordance with the input electrical signal. What will happen? The driving circuit drives the light source in accordance with the input electrical signals. Then electrical variations are converted into optical variations. That optical variations are coupled to the optical fiber. And this is the coupler or connector, and it will travel to the receiver end. At the receiver end, we are having a photodetector. What is the role of photodetector here? The photodetector converts the optical variations into electrical variations. The photodetector converts optical variation into electrical variations. Those electrical variations are given to the amplifier. That amplifier amplifies the signal. Then those are stored in the signal restorer for further processing. So that is about the total optical fiber communication system block diagram. See each block, what is the role we have discussed here. From the signal restorer, we can take the output signal, and for that, after that, it will convert into audio or video based on the what the input we have given. Next, we are going to discuss about the advantage and disadvantage of optical fiber communication. The advantage of optical fibers when compared with the copper cable, one is a much wider bandwidth that we already discussed from starting onward, high bandwidth, 10 gigahertz around, and very high information carrying capacity, and less attenuation, small in diameter and size, so they are lightweight, low cost as compared with the copper. This will happen when we are producing in bulk. Okay, the high number production only make it less cost. And greater safety and immune to the EMI, RFI, and moisture and corrosion. EMI means electromagnetic interference. RFI means radio frequency interference. This interference occurs in case of copper cable because the copper is a conductor. So this electric field creates some EMF induction in the fiber, in that cable, that creates the disturbance signal. That will not happen because optical fibers are insulated. Those are dielectric materials. For example, if you take silica, SiO2, it is dielectric material. That's why there is no chance of electromagnetic interference. There is no chance of radio frequency interference. There is no problem with moisture or corrosion. So then, because these are dielectrics. So next, they are flexible, so easy to install in tight conduits. That means you have to connect them or you make them to permanently couple with each other. Then we have to insert them in a tight conduits. That is easy for us because of their flexible and dielectric in nature. That's why high. That means wherever the electrical sensitive areas are there, so there also we can use these cables because they are dielectric in nature. So electrically sensitive surroundings also we can easily light down. And difficult to tap fibers because that's why they're highly secure. No crosstalks and disturbances, because if you take the copper cable here, when the signal is propagated to one copper cable, then some current is flowing that cable that creates some EMF because of magnetic field developed around that one. That EMF is induced in the neighbor cable. then the disturbance occurs. That kind of disturbance is not possible here. There is no chance because these are insulators here. And different characteristics of the fiber, what kind of advantage we can achieve with this fiber. If you observe here, thin diameter that leads to less space use here, easy to installation, and easy multi-fiber cabling here. When lightweight makes into easy multiple fiber cabling and easy installation, easy bending, that is easy installation, noise immunity, there is no interference, that means RFI or AMI, and low loss, that's why long repeatless range. So that's why need not to install more repeaters because each repeaters are very costly. That is not even that is not required. And wide bandwidth that leads to long repeatless range and large capacity transmission lines. These are the advantages of the optical fibers here. And coming to the disadvantages here, the terminating equipment is costly as compared to the copper equipment. That's why the total communication system becomes very costly. And optical fiber is delicate so as to handle very carefully. And communication is not totally in the optical domain. So that's why always we have to convert the electrical to optical, optical to electrical. So till now, the communication is not coming in the optical domain. Wherever if you want to send a signal, we are getting electrical signal. That we had to convert into optical. Wherever we want to amplify, we don't have optical amplifiers. That's what we are doing. We are converting again that optical signal to electrical signal. We are amplifying and again converting electrical to optical. That's why that system became totally costly also. And optical amplifiers, splitters, multiplexes, demultiplexes are still in developing stages. That was not developed. That already explained. And amplifiers are splicing is specialized technique and needs experts. That means splicing means permanently joining two fibers. For suppose if you want to join one fiber with other fiber permanently, actually by using a connector, in that connector we are inserting the cable from both sides. Then that connector connect this one. But that is the temporary. If you want to connect the one fiber with other fiber permanently, we have to do a welding, that is soldering like this. So we have to keep both the fibers like this, both iron comes in contact, then focusing a laser beam, we make them to connect together permanently. That kind of connection is called splicing. Splicing only experts can do. So experts, if you want to hire, then definitely we have to pay more salary. That's why that communication system becomes very costly. The splicing and testing equipments are very expensive as compared with the cup. So these are the disadvantages. With this, we will stop the lecture today here. Thank you.